So we're slightly early, but carry on. So we've seen a number of presentations this morning and this afternoon, and a lot of them have had in common aircraft. So we're looking at lightning strikes to aircraft, indirect effects, electromagnetic coupling into the aircraft. We saw some pictures of damage directly by thermal properties, so you've got wings being blown apart and holes in the structure and so on. And that is actually the topic of my talk. I want to look at coupled electromagnetic and thermal effects caused by lightning strike on aircraft, but in particular on carbon fiber composite materials. So this is something that is being used more and more in aircraft construction, and I suppose in things like wind turbines, which might also be exposed to lightning. Right. So we've got a statistic. It's the Federal Aviation Authority in the U.S. claims that on average, every commercial airliner is hit by lightning once a year. Okay. Given the pictures that we saw earlier, this is of a little bit of concern to those sitting inside the aircraft. And we hope that the mitigation measures that have been designed will actually protect the aircraft and us from any bad things, I suppose, or bad effects. To design these mitigation measures, we're increasingly making use of simulation, as we've seen. If we take into account another trend over the last few years, and that is the increased use of carbon fiber composite materials in aircraft construction. For example, we can see, you can't see, but that says 1980. We started off with the first use of carbon fibers in aircraft, very small amount, 5 to 6%. The trend has been an increased use. In 2005, the Airbus A380, over 20% of that aircraft was constructed of composite materials. You'll see that it's a lot of different components, but not, as in the Boeing 787 Dreamliner, the main critical components like the fuselage, which houses the passengers, or the wings, which house, for example, the fuel. So really critical components are now being constructed to a large degree from carbon fiber composites. The mitigation measures luckily do seem to be working thus far. Okay, so this is a Boeing 787 prototype, was hit by lightning accidentally. It wasn't planned in June 2010 and survived apparently, so that's quite good news. But the use of these carbon fiber composites, the aim is to increase the efficiency of the aircraft flying. We want to reduce the weight, increase the fuel efficiency, and to do that we obviously want to optimize the mitigation measures. So we don't want to use so many mitigation measures that you're adding so much weight that you're losing the effect of saving the weight in the first place. And to do that, we really need to understand what these materials are made of. If we want to simulate them and understand how lightning is going to affect them, we have to understand, for simulation in particular, the fine structure. And for carbon fiber composites in particular, the material is actually fairly complex. And from a simulation point of view, that can be quite problematic. So we start off with a number of very narrow fibers. You can see there's 1 micrometer, is that little distance over there. Thousands of these are taken, they're woven together to form some kind of yarn, as shown at the bottom left. And that yarn is then woven together again to form sheets, as shown at the bottom right. Those sheets can have different orientations. They can be unidirectional, as shown here. They can also be bidirectional, so woven across like this. But the key about them, especially in this configuration, is that they have a very high, or let's say relatively high, electric and thermal conductivity along the direction of the fibers, so along the direction of the weave. A very low, or relatively low, again, conductivity across the fibers, so along, in this case, horizontally across the screen, and also low through the fibers. Okay. So it's a very anisotropic material, and from a simulation point of view, this is key. An added complexity is that you're taking a lot of these fiber sheets and you're arranging them on top of each other. You're gluing them together with epoxy, and they've got alternating orientations to increase the strength. And so you end up with a material that's really fairly complex from a structural point of view and also from a simulation point of view. We'd like to understand how these materials behave when struck by lightning. And of course, we can have a look at the airplane once it's landed and see, did it survive or what was the actual damage. But in controlled conditions in a laboratory, we can also gain a lot of information. So a typical test setup would be to position a piece of this carbon fiber stack up in a test jig, as shown here. So we've got a ground plane, the copper ground plane. On top of that, you've got the stack up. Above that, you've got an impulse current which is being injected, which simulates your lightning response. That can have any waveform you like. In this case, we're using the first return stroke, so sort of a double exponential waveform. You can obviously specify the current strength, up to 200 kiloamps, as we heard earlier, but maybe even more, 250. Typical lightning strikes in Europe, by the way, are about 10 kiloamps, apparently. The material here, since we're looking at localized effects, we want to know on a local scale what is the heating and the damage going to be. And so it's important to include the fine detail. We need to know, as we saw in the previous slide, we have to include the anisotropic effects of each layer, the different epoxy material properties, and so on and so on. I'm just going to skip back a slide because I just forgot to mention something. You'll notice I didn't mention any numbers here, and that's partly intentional. The point is that knowing these numbers is very important to simulation. Obviously, getting the material properties right is critical to getting sensible values. And I say high, low, low because it's not particularly well understood, and it differs from material sample to material sample. So those numbers are really up to the user of the software, so the designer, to discover, to measure probably, and to use in their simulations. Going forward again, if we want to understand, if we want to understand how this, if we want to run a simulation, sorry, getting a bit confused. If we want to run a simulation, we obviously have to know what output we are interested in. Okay, so it's all very well setting up a simulation and running it, but if you don't know what you're looking for, you don't know how to define the whole setup. Okay, so to understand what we're looking for, we have to understand how the structure is going to respond and what the damage mechanisms actually are that are responsible for potential failure of a carbon fiber plate. Here are two photographs, well, one photograph actually, thanks to EADS Innovation Works, by the way, for the photograph. Just to mention, so it's a painted carbon fiber stack up, no lightning protection at all, and that's the aftermath of a lightning or controlled strike to this by a high current. Interestingly, the first thing is you can see that the damage is along a particular axis, which just shows us, okay, there's some kind of anisotropic effect going on here. The second thing, so in order to understand the damage mechanism a bit more, one quite interesting property, one interesting effect is that it's not confined to just one layer. Okay, so that means that it's not just a purely electrically conductive effect. If it was only electrically conductive, all the energy would be dissipated in the top layer because there's a negligible conductivity down through the material. So one can hypothesize what's happening. I think it's not particularly well understood exactly what mechanisms are at play, but there's a very interesting paper. If you turn your heads like this, you can probably read this. It's a paper by Ogasawara et al. And it discusses this whole problem that I'm showing here. And they hypothesized that there's a lightning strike to the surface of the carbon fiber that causes some kind of localized heating effect. Above a certain temperature, there will be, basically the matrix resin will delaminate, so there will be a gap between the different layers. There will be some kind of pyrolysis gases formed because of that decomposition. And then there's going to be a dielectric breakdown across to the next level, leading to some kind of current flowing into the second layer, okay, and so on. As this heats up further, you've got another effect coming in. So above 3,000 degrees Celsius, roughly, the carbon itself, sublimation of the carbon itself occurs, and it actually starts physically breaking apart. So you see this sort of effect over here. And then you've got direct conduction of the lightning through to the lower layers. Okay. Obviously, this is, this sort of complex behavior, it's pretty much impossible to simulate that in all its complexity. But a good starting point is to look at the temperature. And the reason for that is that it can be shown that the temperature increases. So here we've got simulated temperature increases on the surface and at the interfaces between the different layers. There's a very close correlation between the temperature increase and between damage, which is shown on the structure itself. So if we can run a simulation which shows us how much the structure heats up if it's exposed to a particular lightning strike, we can hopefully predict how the material will respond. and then also design mitigation devices to reduce the temperature. Right, so now we come finally to simulation with Microwave Studio, or not Microwave Studio, but the different tools within CST Studio Suite. The first step, of course, is to discover what the current distribution, what the power in the structure is doing. So we need to run an electromagnetic analysis. We've got a number of tools at our disposal. So there's the high-frequency tool, F-solver, the full-wave low-frequency solver, and also the static current solver. Both of these two on the right are in CST EM Studio. The key point of all of those is that they need to be able to consider fully anisotropic materials. And that's something which is quite new in CST. In fact, version 2011, we were able to consider the full tensor representation of the anisotropic materials for the first time. Excuse me, the water. In any case, we end up with some kind of current distribution. We can then calculate from that, if we know the material properties, we can calculate the thermal loss distribution, so basically how the power is distributed through the materials. Of course, we need a very good knowledge of the material properties. Coming back to the high-low from a few minutes ago, you really need to know exactly what those material properties are. And finally, we can use that to run a thermal analysis in our thermal solver. That can be static or transient. The fourth step, and I put this in brackets because I think for a structure of this complexity, it's not really feasible, but for a lot of structure types, it is. You can actually use the structural solver to calculate the mechanical deformation of a structure due to the thermal effect, thermal heating effect. So that's something, maybe not for this case, but in principle, we can do this as well. So we've got 1, 2, 3, 4, 5, 6 different solvers. So which approach should we use? So in the example that I'm showing here, I'm going to start off with a static solver, and then use that and then use the transient thermal solver to take into account the lightning waveform that we've seen so much in the last few hours. Static solver, you can kind of justify this by simulation, you can show that the current establishes itself inside a structure of this size. Remember, we're talking about quite small structures here. I think the sample was maybe about 100 millimeters by 100 millimeters. The time that it takes the current to establish itself is much quicker than the rise time of the lightning stroke. So a static approach to calculate that distribution is probably not too bad even. And then we can really take into account the transient effects with a thermal solver. So we can construct a model in CST Microwave Studio. So very, very simple, kind of a reduced model. We've got 4 layers. I'll zoom in on those in a little while. The most important thing is that we're injecting current through some kind of path. So this could be your probe head. You might want to replicate what you actually have in the laboratory. It might be the same dimensions as a typical lightning strike. So here I've chosen the diameter of 5 millimeters for that. I think the typical lightning strike is ½ inch almost, or something. Perhaps the lightning expert or the physicist can tell us a little bit more about the precise shape. But I think 12 millimeters is a value that you can find on the internet. And the power that we're using is the typical European lightning strike magnitude again, which is about 10 kiloamps. As I said, we're focusing here on the first return stroke, but you can look at any part of the behavior. So there's a lot of energy deposited during the static part. So once the channel is established, most of the energy is deposited in. So you could simulate that part as well. Around the edge, we have a ground plane. Okay, and this actually forms the discharge path for the current flowing through the carbon fiber stack-up. And finally, if we zoom in here, we can look at the fine structure. So we've got 4 layers of this carbon fiber. Each one is type anisotropic, 0.2 millimeters thick, and they're bonded together by 3 layers of epoxy, which are about ½ millimeter thick. We've given the epoxy a small conductivity just to represent the fact that there will be some contact of the fibers through the epoxy. So it's not perfect stainless sheets. The geometry it has some kind of tolerance in it. So we've got an effective conductivity to represent that. And if we just focus a little bit more on the material properties, so each of these objects has got an conductivity which is directed in a different orientation. And so to construct this can be a bit of a problem, but in version 2011, we've made this a lot easier in EM Studio. What you can do is you can assign a local coordinate system to each object, and you just have a single material property, and depending on the orientation of the local coordinate system, that material property is then applied to the individual objects. So you can see here in the first layer, this conductivity of, I've just chosen a value here, so 100,000. I think that's the conductivity of graphite, so we've just chosen that. That conductivity is U-directed. In the second layer, it's also U-directed, so it's overall directed in this along the Y-axis. In the third layer, it's pointing diagonally in that direction towards the back of the object, and in the fourth layer, it's pointing horizontally towards this corner of the object. Okay, so we've got these 4 different layers, and it's quite easy to set these up in EM Studio 2011. And what you get at the end, so if we now run the J-static simulation, you get, in the first layer, current flowing purely U-directed, so U-prime directed. In this case, it's in this orientation. So you can see that its current is nicely directed along the conductivity. The reason that the band is so wide is that the injection point is 5 millimeters, and the overall length here is only 100 millimeters. So it's actually quite a large, well, it is in fact this width. So that's why you've got this wide band. In the second layer, so some current is flowed down through the epoxy into the second layer, and you've got it flowing horizontally out. Again, you can see how the local axis is always changing, so it's always U-directed effectively. In the third layer, current flowing diagonally. In the fourth layer, again diagonally towards the other corners. So you can really nicely see the anisotropic current flow in the different layers of the material. The next step is then to take this current distribution, calculate the thermal loss distribution, as shown here, and then to inject that into or to excite the structure in the thermal solver with that power loss distribution according to our double exponential waveform. In fact, because the current has a double exponential waveform, the power will have the square of that. So it'll be a squared double exponential waveform, and that's actually what we're using to excite the structure. And you can see really nicely how the heating of the structure, this is in the first layer, 0.5 millimeter below the surface, how that really follows. You can see the anisotropic effects very nicely indeed. Right. So in conclusion then, actually, just before I get to the conclusion, this is a bit of a simplified representation of the whole thing. So in fact, we're assuming a single current or a single current distribution, where actually the conductivity, as we just saw in the previous talk, the conductivity is dependent on the temperature. So in principle, as this heats up, we should be changing the conductivity and then, continually updating the power loss distribution in time, and that will lead to a different temperature or a different heating effect. So this is something that isn't taken into account in this example that we've calculated here, but is something that we can do in principle now. We have all the tools in place, and that will be made much easier in upcoming versions of Microwave Studio, or of Studio Suite at least. So to conclude, the first point, I think, is that it's a very complex problem. So there's some complex physics and complex mechanisms going on there, and we can't really hope to simulate that in its entirety. But you can simulate some very relevant parts. And in fact, you can take into account complex behavior like this by effectively changing the material properties that you use in the simplest simulations. So for example, here, as this thing heats up, you're having these physical effects like this dielectric breakdown and finally the breaking of the carbon fibers themselves. What's happening effectively is that as this is getting warmer, the conductivity is going up. So if you can simulate thermally dependent conductivity, you could kind of approximate this effect. But the key is that we can really now, with the current tools, simulate physically relevant and significant phenomena. So we can simulate how these structures heat up. What that allows us to do is to design ways of preventing them from heating up, so improve the design of the mitigation methods, and that for these complex materials. And finally, I think one important point is that all of these solvers that may be required to look at these complex systems are in one intuitive, well, in one interface at least. And that's maybe, it's a point that is underestimated sometimes, is the actual overhead in setting up a problem and allowing the linking between the different electromagnetic and thermal simulation. And as I mentioned a moment ago, in upcoming versions, because they're already in one interface, it'll be much easier to link between them and sort of, going from a static to a thermal transient, back to a static simulation, back to a thermal simulation. So these loops that allow you to feed back properties, property changes, and so on will be much easier to implement. Yeah, that's all from my side. I'd just like to say thanks to Simon as well for your input and the kind of stimulus that you've provided here. And that's all from me. Are there any questions at all? Any questions? Okay. Fine. I know that there's some shortcut for skipping to this slide, but I don't know. I'm not sure what it is. Yeah, I mean, it's basically these strands are again woven together to form these strips over here, shown on the right. So those are really, originally they're individual fibers, then they're in these yarns, I think, or strings, and these are then formed into sheets like this.
Okay, thank you, Marc. Yeah, the last two presentations will come now from the US, and therefore we would also like to activate now our video conference system.